Hello everybody, my name is Konstantinos Korgiopoulos and I'm a PhD candidate at McGill University in Montreal, Canada. Today I'm going to talk about my research on magnesium alloy development. Actually, in my research I'm trying to reveal the secrets behind the ductility improvement in magnesium alloys by adding different elements from the periodic table. But you may ask, why magnesium? Why do you care about magnesium? Magnesium as a metal is very light, and you can actually make really light alloys that can be used in automotive parts, and this can reduce the weight of vehicles. Just imagine that magnesium is around 30% lighter than aluminum, is around 60% lighter than titanium, and 70% lighter than steel. But why is it important to reduce the weight of vehicles? It's really essential because by using magnesium, that offer actually a viable solution in reducing the CO2 emissions, reducing the fuel consumption, or even increasing the efficiency of electric cars. Just imagine a car that it's too light and your battery is going to last more in the car. So everything starts here from the computer where we start with a literature review, we see what other researchers have done, and then we start having an idea of what we would like to do. But we would like to test this idea before actually we make an alloy, and for this reason we are running some simulations, some thermodynamic simulations that can show us what we could expect by making this alloy. So what kind of phases we have, at what temperature is what. So here I have an example of these calculations that can give us a lot of information, and after that we can go in the lab and start synthesize the alloy and then casting it. So here we are in the Light Metals Research Lab of McGill University, and this is where the heart of my research is. Because here we're going to synthesize the innovative magnesium alloys for my research to use it eventually in automotive applications. Everything starts with a magnesium ingot, pure magnesium ingot like this one. You can see how super light it is. We're going to cut it in smaller pieces, and then we're going to add different elements of the periodic table to synthesize the alloy and make new components. But before we start anything, the most important thing is the safety. So here you can see I have transformed. Now we can actually start the research, but first I would like to explain what I'm wearing. So we're starting with safety shoes that are going to protect us from any heavy object that that we could throw on the leg. We have a flammable-resistant lab coat because we're going to handle liquid metal. We have high-temperature gloves that it's really important before we touch anything because the temperature that we're using here are around 700 degrees. Safety glasses, of course, we want to protect our eyes. And then the safety helmet that it has an extra protection to protect ourselves from any liquid metal spill. Other than PP, there are also other safety precautions we need to take in a foundry, in a metal lab, and this is the extinguishing methods. Here you can see a general extinguisher, class ABC, but this cannot be used in a metal fire, but we should always use class D extinguisher. But this is not always necessary, because if we have a small metal fire, we can use sand. This is a specific foundry sand, and it can extinguish really easy any spill of magnesium. We have already done some thermodynamic calculations, so we have an idea what we would like to make. And here I'm calculating the charges to make the specific composition that we're going to use. So here you can see actually the pure magnesium pieces from the billet that I showed you before, pure aluminum pellets or granules that we can use to prepare the charge for the alloy. And here I have the magic element of my research, which is the yttrium. And we're going to use trace amounts of this element in order to modify our alloys. So for my calculations, I need to measure how much of charge we're going to use. We're using the scale here. And then when we are sure that we have the correct amount, we can go and synthesize the alloy. Here is the experimental setup that we're going to use to synthesize the magnesium alloy. It consists of an induction furnace, and here we have a graphite crucible that we're going to melt to prepare the melting side. We also have a thermocouple that is going to control the temperature. And of course we have a protection gas supply, because magnesium can ignite at high temperature, so we want to make sure that we don't have any issue. And of course we also use a fuel hood in case that we have any fumes and we would like to take them out. So here, before I start the furnace, I'm going to add some charge inside the crucible, and then we are ready to start the furnace, start the gas, and for the whole procedure I'm going to start adding little by little all the alloying elements, and then we will be ready to cast.
A few moments later.
The alloying additions. We may have some fire because of the oil, but this is fine. It's going to extinguish by itself. I'm going to cover it for a while. It was just a reaction because of the oil. The material was kept in mineral oil, so there were some. There was a small amount of it. But you can see here that now we have all the elements inside. We can stir. So I throw the remaining, we had some remaining, I throw it here. You see how stable it is? The mold was already preheated from before. So I can close the protection. We can wait for a couple of minutes and we can open the mold to see what we have already made.
Moments later.
So here, this is the part, this is the magnesium part that we cast, and actually we can use this part here to make to make samples for mechanical testing, like compression samples, or for microstructural characterization, XRD, different techniques that you will see. So from a mold like this one, we can take a plate like this one, and we can use this part to machine samples for mechanical testing, for microstructure analysis using scanning electron microscopy, transmission electron microscopy, and so many different techniques. Here we are in the mechanical lab, where we are going to test the mechanical properties of the samples, and we are going to evaluate its performance. For this region, we have machined tensile coupons out of this plate, and we are going to use these coupons inside this equipment, where we are going to apply uniaxial load, and this, the sample will break at some point and will be like this one. And this can give us valuable information about its performance. During my research, I spend a lot of hours in this lab because we need to prepare the sample to perform different experiments like microstructural characterization, etc. So everything starts again from this plate. We can cut small pieces, and then by using a cold mount resin, we can mount it here. This sample, we will take it and we will grind it, because we want to make a flat surface without scratches, without anything. And then we will start grinding with finer paper, silicon carbide paper. We will continue with polishing of the sample, and our target is to create a mirror surface. After preparing the sample in the metallographic preparation lab, we are coming here and we're going to use this really fancy equipment, which is a scanning electron microscope. Actually, this equipment allows us to observe the microstructure of our alloy. So what is a scanning electron microscope? Actually, the idea is that we have a source here. This specific one is a tungsten source that creates electrons, and these electrons interact with the sample, in this case the magnesium alloy, and we can get these amazing microstructures. So here in this microstructure we can see the magnesium matrix. Actually, it's so nice because we can even see the grains and we can see these nice features. And actually, for my research, these features are really important because they can determine the mechanical properties. So my aim is to modify this microstructure to be able to improve the mechanical properties and actually to increase the ductility of my alloys. Another interesting fact about this microscope is that we can know exactly what is the chemistry of these features that we observe here. And this can be done by using the X-rays. So we have an EDS detector that you can see here, and it is showing all the elements from the periodic table that exist in this microstructure. So in this case, actually, we can see that we have magnesium, aluminum, yttrium, some manganese, and some iron in this alloy. Scanning electron microscope is an amazing tool. It's easy to use, and it can give very valuable information about the microstructure. This is another part of my research. This is called X-ray diffraction, or XRD, and I'm using it to characterize the crystal structure of my material and if there is any change in that after adding different elements in magnesium. How does it work? Actually, there is an incident X-ray beam that goes inside the sample, and then some part diffracts back. And with a detector, we can collect the signal and we can analyze it. These are some typical results we get from XRD, and this can give us information about the crystal structure of the material, and we can also identify the phases that we have. For example, in this alloy, we have a magnesium aluminum phase, and these actually can be shown in the diffraction peaks. Of course, there are other parameters that are important for my research, such as the lattice parameter, that can be changed by adding different alloying elements inside magnesium, and this can improve the mechanical properties of the system. So, to wrap up with what we have done today, when you make research, you need to use different techniques to combine them in order to have a story and really understand what's going on. From these results, we know that the trace additions that we added in magnesium alloys, they have actually worked, they have improved the ductility of the components. So now we are at the stage of trying to understand why, which is the mechanism that improved the mechanical properties. And for that, we also need more complicated techniques like transmission electron microscopy, atom protomography, etc. So after all this, you may ask me, what motivates you to wake up early morning, come in here, pursuing your PhD, doing experiments and all this kind of crazy stuff? You know, I always answer that to myself. And for me, it's something like curiosity. I'm curious for everything. We're living in a world that we're surrounded by materials. Everything is materials. So even if you want to improve something in engineering, let's say, in mechanical engineering, electrical engineering, again, you have to improve the materials in order to go one step forward. And another thing is that you start with a question, a research question that you want to answer, and then somehow you ended up with thousands, hundreds of questions that you are really willing to answer. And this is actually what makes me be here, to be curious, to answer these questions, and makes our life better. Because magnesium actually is a light metal. Magnesium alloys are light alloys that can be used in, as I mentioned before, to decrease the pollution. They can be used in medicine to, for example, make stents for the heart. It can be used in electronics. It can be used everywhere as a structural component. And this can offer a lot of viable solutions for our planet. Thank you very much for watching this video. I hope you learned some things about my research here at McGill, and you learn more things about magnesium and how important it is to develop new alloys. And I hope I will see some of you here in McGill University to pursue a degree. Thank you very much.